This is Lecture 2, Collecting and Measuring Data. By the end of this lecture, you should be able to understand how researchers measure concepts in quantitative political science research, write a variable's operational definition, classify and describe a variable based on its unit of analysis, evaluate whether a variable measures a concept in a valid and reliable manner, compare variables that measure the same concept in different ways, and read and comprehend the information in an SPSS dataset. In the previous lecture, I briefly reviewed the basic steps in conducting a statistical analysis in political science research. Before I go into more detail on how to conduct statistical research in political science, first I need to teach you how to measure concepts and variables. If you do not know how to measure concepts and variables, you will not be able to conduct any statistical analyses. Hence, this lecture is all about collecting and measuring data. Political scientists study concepts such as liberalism and conservatism. These concepts are not tangible. You cannot touch them or hold them in your hand. You cannot see them. You cannot hear them. Nevertheless, we know these concepts exist. They exist as mental constructs. Since these concepts are mostly mental constructs, we have to make sure we have a good definition of what they are if we want to measure and collect data on them. For example, we know some people are liberal and conservative, but what does that mean exactly? Typically, we define liberals as individuals who believe the government should play a large role in economic issues, but a small one in social issues. And conservatives are individuals who believe the government should play a small role in economic issues and a large one in social issues. Another example is the difference between democracies and dictatorships. Typically, we define democracies as countries where officials are elected through free, fair, and regular elections, while in dictatorships, leaders are selected through other means, such as through force, military advancement, or through the single ruling party in the country. Another example is war. Typically, in political science, we define a war as a violent conflict between two or more countries that results in 1,000 or more battle deaths. Certainly, there are issues with this definition, because a conflict with 900 battle deaths might be similar to a conflict with 1,000 battle deaths. But without being specific about defining what a war is, it becomes difficult to distinguish between short-term skirmishes between two countries and serious violent conflicts. So the 1,000 battle deaths criterion just makes it easier to identify serious conflicts. So in this lecture, I'm going to review the process political scientists typically use to measure concepts. In order to properly measure a concept, we have to write its operational definition. The operational definition tells us how a concept is measured. The operational definition includes the unit of analysis. The unit of analysis tells us which individuals or groups the data apply to and when. The operational definition also includes the values the variable takes, what those values mean, what we have to observe in the real world to determine the value each observation takes, and the source of the data. Here is an example of an operational definition for a democracy variable. The unit of analysis is countries in the year 2017. The variable takes on the values 0 and 1. A 0 means non-democracy and a 1 means democracy. In order to determine if a country is a 0 or 1, we establish the following criteria. If leaders are selected in free and fair elections, where every adult can participate and the rules do not favor one party over another, and leaders must face re-election at fixed intervals, the country is coded as a democracy. Otherwise, it is coded as a non-democracy. And the source of the data is the CIA World Factbook. The first step in writing an operational definition of a variable is identifying the variable's unit of analysis. Recall that the unit of analysis tells us who the variable applies to, which individuals or groups, and when they existed. The who of a unit of analysis could include a lot of different types of individuals. It could be individuals such as survey respondents, students, candidates, legislators, or judges. The groups of a unit of analysis could include a lot of different types of entities. It could be political parties, countries, or international organizations. The when of a unit of analysis tells us when the individuals or groups existed in time. It could be in days, months, years, or even centuries. Using our democracy variable as an example, our unit of analysis is countries in the year 2017. The next step is establishing the specific observable criteria for your variable. For example, if we were measuring democracy and we wanted to measure elections, we would specifically examine whether a country has free and fair elections, where every adult can participate and the rules do not favor one party over the other. In addition, we will want to make sure leaders are held accountable. One observable and measurable way leaders can be held accountable is having to face re-election at fixed intervals. The next step in creating an operational definition is identifying the values your variable will take and what those values mean. For example, with our democracy variable, we can make a rule that when we identify a country as democratic, meaning it has free and fair elections and leaders face re-election at fixed intervals, we can give it a value of 1, and all other countries will receive a value of 0. The last step in creating an operational definition is defining your data sources. Your data sources tell you whether your subjects meet the specific observable criteria in your variable. We could either use data we collected, which is called primary data, or use data that other people have collected, which is called secondary data. If we wanted to collect primary data, we could use information from news reports, government documents, surveys, or experiments. There are lots of places we can collect data from. Of course, there are a ton of political science-related data sets out there that other scholars have already created, so often it's just easier to use data other people have created instead of creating our own. This is known as secondary data. So in our previous example, we stated that we would classify a country as democratic if it had free and fair elections, where every adult can participate, and the rules do not favor one party over the other. In addition, leaders in the country have to face re-election at fixed intervals. We could use the CIA World Factbook as a data source in this case to determine if different countries throughout the world meet these two criteria. The variable we created would be a primary source as we collected it. And here is the operational definition of democracy in full. In this class, we will typically not write our own operational definitions of variables and will not collect our own data to conduct statistical analyses. Instead, we will use data other researchers have collected to conduct statistical analyses. But before we do that, we must understand what data is available and how to read it in the statistical software program we will use in the course, SPSS. So let's imagine it's the end of the course and you want to conduct a statistical analysis that focuses on term limits for state legislators in the U.S. states. So you would need a data set that has data on the U.S. states that includes a variable for term limits. The 4 data sets available for analysis in this class are the GSS, the NES, states, and world. The GSS and NES are surveys of individuals. The states data set is a data set with data on the 50 U.S. states. And the world data set is a data set with data on countries throughout the world. So if you were conducting a research project on term limits for state legislatures in the U.S., the best data set to use is the states data set. So the next step is to see if there is a term limits variable in the data set. When you open up the states data set in SPSS, this is what you will see in the Data View tab. The columns in SPSS are the variables. The first column sometimes tells you the unit of analysis, but sometimes it does not, and you just have to know what the unit of analysis is. So for example, we know the states data set is measured at the state level, so the unit of analysis is US states. Next, the rows are the observations, and the cells include the data for each variable for each observation. So for example, this column here is the data for term limits, and now we know there's a term limits variable in the states data set. And we can see that the value of term limits for observation 1 is 0. But we don't know what a 0 means. If we scroll down, we notice that term limits could also take on a value of 1. What does that mean? To find out what the 0s and 1s mean, we have to go to the Variable View tab, which is located at the bottom of the SPSS screen. In the Variable View tab, the rows are the individual variables. The name tells you the name SPSS uses to recognize the variable in statistical analyses. The label gives a more realistic description of the variable. The values column tells you the values of a variable if the variable has categories. And if we click on the gray box within the values cell for an individual variable, a screen pops up that tells us what the values mean. So for example, the term limits variable is coded 0 for states without term limits and 1 for states with term limits. Note that if the variable is measured in continuous units such as dollars or percentages, the value cell will be empty. You can go back to the Data View tab to see what values the variable takes. Also, the missing column tells you which observations of a variable SPSS ignores in an analysis. So for example, sometimes researchers code an observation as a -9 to denote that information for that observation is missing and it should be ignored in an analysis. Also of note, if you are having problems understanding what the unit of analysis is of a variable, or how the variable is measured based on the information in the dataset, you could always read the code book for the dataset to find this information. If you do not know where the code book is, you could always Google the dataset name to see if you can find it that way. Luckily, your IBM SPSS Companion to Political Analysis has the code books for all of the datasets in appendices A1 to A4 at the end of the book. When you read these appendices, make sure to read the main text and the footnotes for more information. So now that we know that the states dataset has the term limits variable and we know how to read the information in the dataset, we can use the information from SPSS and the code books to write the operational definition for the term limits variable. Recall that the operational definition includes information about a variable's unit of analysis, tells us what values the variable takes and what they mean, what we have to observe in the real world to determine the value each variable takes, and the source of the data. For the term limits variable, we know the unit of analysis is US states. And since there's no information about the year and the dataset was released in 2020, we can assume it applies to 2020. And we know from SPSS the variable takes on the values 0 and 1, with a 0 meaning no term limits and a 1 for term limits. The only information we haven't figured out is how the authors of the dataset determine this. If you go to the code book in the back of the IBM SPSS companion to political analysis book for the state's data set, and you find the term limits variable, there is a footnote that tells you that the data is from the NCSL website. The NCSL is the National Council of State Legislatures. So now we know that the authors of the dataset used information from the NCSL to determine whether a state is coded as 0 or 1. And last, we know the source of the data is the state's dataset, a secondary source since we did not collect it. After we write our operational definition and collect our data, we can classify what kind of data or variable we have. This classification will be based on our unit of analysis. Recall that the unit of analysis tells you who or what the variable applies to, which groups or individuals, and when those groups or individuals existed. Based on the unit of analysis, you can classify your data set or variable as either a case study, cross-sectional, time series, or cross-sectional time series variable or data set. This chart here can help you determine what kind of variable you have. If your variable only applies to one subject and you only have a few observations for that subject, then you have a case study. An example of this would be studying democracy in the U.S. in 2017. There would only be one subject, the U.S., with a couple of observations in 2017. If your variable only applies to one subject, but you have multiple observations for that subject over time, then you have a time series variable. An example of this would be studying democracy in the U.S. between 2001 and 2017. There would only be one subject, the U.S., with multiple observations between 2001 and 2017. If your variable applies to many subjects and you only have one observation per subject, then you have a cross-sectional variable. An example of this would be studying democracies in all countries throughout the world in 2017. There would be multiple subjects, all countries in the world, with one observation each in 2017. If your variable applies to multiple subjects and you have multiple observations of them over time, then you have a cross-sectional time series variable. An example of this would be studying democracy in all countries throughout the world from 2001 to 2017. There would be multiple subjects, all countries in the world, with multiple observations each between 2001 and 2017. Going back to our democracy variable, our unit of analysis was countries in the world. In the year 2017, in our variable, we would have observations for multiple subjects, all countries in the world, with one observation each, 2017. This would make our variable a cross-sectional variable. After we collect our data, we have to review our variable to make sure we are measuring what we want to measure. A variable is valid if it measures the concept it intends to measure. It is invalid if it does not measure the concept it intends to measure. It matters if our variables are valid measures of our concepts. If a variable does not measure what we want it to, then we may draw false conclusions in our analyses. In addition, since different variables measure the same concepts, for example, there are several different measures of democracy, we are able to compare the validity of these measurements in order to be able to choose the most appropriate one to use. For example, imagine development could be measured on a 0 to 10 scale, with 0 meaning least developed and 10 meaning most developed. And imagine we knew that the true value of development in country A was 5. Then imagine we created two different variables that measured development. The first variable coded country A as a 5, and the second one coded country A as a 3. Clearly, development variable 1 is a more valid measure of development because it more closely measured the true value of development in country A. There are several reasons why a variable may be invalid. For example, systematic measurement error occurs when we create an operational definition that consistently mismeasures our concept for a specific reason. One reason could possibly be that the variable measures more than we think it measures. For example, going back to our democracy variable, we said we would use data from the CIA World Factbook to determine if countries had free and fair elections and leaders faced elections at fixed intervals. If the CIA World Factbook is an unbiased source of information of countries throughout the world, the information it gives us would allow us to collect a valid measure of democracy throughout the world. However, if the CIA World Factbook is biased in such a way that it is less likely to publish unflattering information of U.S. allies, then our variable may lead us to code some non-democratic countries that are U.S. allies as democracies. Then our variable would not only be measuring democracy, it would also be capturing U.S. government bias of countries throughout the world, a characteristic we did not intend to measure. U.S. bias is causing systematic measurement error in our measure. If that happens, then our variable would be invalid. The solution to this problem is to find an unbiased source of information to code our variable. The Hawthorne effect also leads to systematic measurement error. The Hawthorne effect occurs when you're collecting data from individuals, and those individuals behave differently because they are being observed. So, for example, we know that when survey researchers ask respondents questions about race-related issues, the race of the survey researcher and the respondent matter. African American survey respondents are more likely to say they face discrimination when an African American survey researcher asks them questions about discrimination versus when a white researcher asks them questions about discrimination. Hence, the survey questions are not only capturing African American attitudes on discrimination, the intended characteristic, they are also capturing social pressure, an unintended characteristic. The solution to this is to have survey respondents fill out a paper survey that is confidential so they don't feel pressure to answer a certain way based on the characteristics of the survey researcher. The way we code our variable could also lead to systematic measurement error. Recall that we coded non-democracies as 0 and democracies as 1 in our democracy example. It is easy to classify countries that are purely democracies and purely non-democracies. But there are several countries throughout the world that are not clearly democratic or non-democratic. Russia is a perfect example. There are elections in Russia, but the leaders are rarely held accountable for their actions. Should Russia be classified as a democracy or not? It is a tough question. In order to overcome this problem, we should probably go back to our operational definition of democracy and refine it. We could add another category to the definition. Democracies could be coded as 1, mixed systems could be coded as 0, and non-democracies could be coded as -1. There are several different ways we can evaluate whether a variable is valid. The two I'm going to talk about in this lecture are face validity and construct validity. Generally speaking, the face validity test is when researchers examine how a variable is measured and determine whether the variable is a valid measure of a concept. Often experts will look for the potential for systematic measurement error in a variable based on how it's measured. If there is potential for systematic measurement error, they may conclude the variable does not pass the face validity test. For example, we could look at our democracy variable and think deeply about whether there may be reasons the variable might miscode some cases. We already did this when we discussed threats to validity in the previous slides. For example, we talked about how it could be possible that the CIA World Factbook was biased and could lead us to miscode some non-democracies that are U.S. allies as democracies. If this is the case, then the democracy variable would fail the face validity test and would be considered an invalid measure of democracy. Next, there is also the construct validity test that helps us determine if a variable is a valid measure of a construct. In a construct validity test, we determine whether our variable is correlated or related to similar variables it should be related to. We could compare our democracy variables to a human rights variable, as we know democracies are more likely to have good human rights practices than non-democracies are. If we compared our democracy variable to a human rights variable but discovered that the two variables were not correlated, our democracy variable would fail the construct validity test. Not only do we need to evaluate whether our variables are valid, we also have to evaluate whether they are reliable. Reliability is the extent to which a variable consistently measures a concept across all observations. A variable is not reliable if it does not consistently measure subjects or cases the same way when we apply our coding criteria to those cases over and over again. Using our democracy variable as an example, the variable would not be reliable if some countries were coded differently by different coders. It would be reliable if all the coders measured the countries the same way. Here is a more concrete example of how reliability works in practice. Going back to our development variable, imagine development could be measured on a scale from 0 to 10, and we know the true value of development for country A is 5. Imagine we use the coding criteria from development variables 1 and 2 to code country A 4 different times. Variable 1 coded country A as a 5 the first time, then 6, then 5, then 4. Variable 2 coded country A as a 3 the first time, a 10 the second time, then 2, then 8. Clearly, development variable 1 is a more reliable measure because when it is applied to country A over and over again, it produces similar values. One threat to reliability is when you have multiple coders coding a variable and they sometimes have to make judgment calls about how to code a particular observation. So, for example, one of the coding criteria for the democracy variable was whether a country's electoral rules do not favor one party over the other. This is not an objective criterion, it's subjective. As such, two coders might disagree over whether a specific country's electoral rules favor one party over another. If that's the case, one coder may code a country as a democracy and the other might code it as non-democracy. One coder would clearly be correct and the other would not be. As a result, the democracy variable would be an unreliable measure of democracy because it sometimes measures democracies and non-democracies correctly and sometimes it does not. There are several different ways we can evaluate reliability. One way is the test-retest method. In the test-retest method, we apply the coding criteria from our variable to the same subjects repeatedly to make sure the variable produces the same coding outcome every time. When we have multiple researchers coding our data, we can use an intercoder reliability score to make sure the variable produces the same coding outcome for each subject in our dataset, regardless of which coder is coding the data. A simple intercoder reliability score is the percent agreement measure. It is calculated by dividing the total number of cases that coders agreed upon divided by the total number of cases multiplied by 100. So in this example, coders 1 and 2 agreed upon the codings for country A, country B, and country D. The percent agreement measure would then be 3, the total agreed upon cases, divided by 5, the total cases, times 100, or 60%. If you do find out that a variable has a low intercoder reliability score, one solution is to have a principal investigator make the final coding decisions for observations that are coded differently by different coders.